It's a great pleasure to have Surjeet here. I've known him for the last 2 years. I heard his various talk. He is a crazy mix of various different parts of physics. Particle physics, some AMO, some low temperature ideas, and then he's a theorist. But if you didn't know, you might think he's an experimentalist. His talk will have a nice flavor, hopefully, of both components. He had his bachelor's from Caltech and PhD from Stanford. Then he has been a faculty at UC Berkeley since 2014. He got the Sloan Fellowship in 2016 and the Breakthrough Prize, New Horizons Prize in 2017. So it's a great pleasure. He's going to tell us something exciting. Thank you.
Thank you very much. Thanks for the nice introduction. Just to set expectations more normal, I doubt this talk will be that exciting that the Secretary of the Energy will tweet about it, but hopefully you'll be entertained. So anyway, I want to talk about some new ways in which one can search for dark matter. Okay, we know dark matter exists, right? We have observed it gravitationally. There's absolutely no doubt that it's a new particle. And as particle physicists, we are very interested in finding out if this particle has other interactions. Pretty much every other particle we know about, other than the graviton, has non-gravitational interactions. So it's reasonable to think that dark matter also has some non-gravitational interactions. If you find them, you'll be able to discover some new sector in physics from which the dark matter is coming from, and hopefully that will allow us to answer questions like, why does it exist? What's its purpose? Things of that sort. So for me, the interesting question is to ask, how do you detect these non-gravitational interactions? What do you have to do to find them? And the challenge, of course, is that these will be very weak effects because the dark matter is dark for a purpose. It doesn't interact much with this kind of model. So how are we going to find these weak effects? Obviously, we're going to need techniques that have high precision to be able to go after these weak effects. The interesting thing is that in the last 2 decades or so, we happen to live in an era when there have been incredibly impressive developments in precision instrumentation. One can today measure magnetic fields smaller than a femtotesla or so through squid and atomic magnetometers, and measure accelerations that are smaller than about 10 to the minus 13 little g, where g is the acceleration due to gravity, and that's due to atom and optical diffraometers. In fact, the slide is a little bit outdated because the LISA Pathfinder experiment pushed that limit to about 10 to the minus 16, okay, recently. And that's part of the theme here, which is that if you ask anyone who actually works in the technology side of the story, they don't really believe these numbers are final. They expect things will get better. Okay, every few years or so, they've been able to beat these limits down by an order of magnitude or so. Right. So this is a field with a lot of rapid technological advancements going on, and one can therefore ask, how can these technologies be used to find dark matter in particular? Right? How do you do that? So what kind of dark matter is actually interesting? Right? What do we find? So naively, you might think, if you ask a theoretical physicist, what could the dark matter be? Naively, you might say, well, the dark matter could have a mass as small as 10 to the minus 43 GeV. That's the Hubble scale, the size of the universe. Okay? Or it could be as big as 10 to the 48 GeV. That's like a macho, right? That's the limit that we have observationally, that the dark matter was heavier than this, it would screw up light from stars. It would bend light too much, and the Kepler observations rule that out. So naively, you would think it could be in this enormous range. Okay? But we are theoretical physicists, and we are paid for a reason, so we can do these. We can make better bounds than this. So let's see how much better we can do. So we can impose, turns out, just one more bound on the mass of dark matter, which is that we know the dark matter must fit in the galaxy. And the fact that the dark matter fits in the galaxy imposes 2 non-trivial bounds on its mass. If it's below 100 eV or so, the dark matter cannot be a fermion, because if the dark matter mass goes down, given that we know its abundance, its number density must go up. So if its mass is below about 100 eV or so, if it's a fermion, you would then have to put too many fermions in the same occupancy mode or whatever, right? So it's Fermi degeneracy that prevents that from happening. So if it's below 100 eV, dark matter cannot be a fermion, but it could be a boson, right? You can pack as many bosons in as you want in the same mode, there's no problem. But eventually, if the mass of the dark matter gets really, really small, its de Broglie wavelength will get really, really big, and eventually the de Broglie wavelength will get bigger than the size of the galaxy, which means it won't be able to fit in again. Okay? And that puts a limit of about 10 to the minus 22 eV on the mass of the lightest boson that could be dark matter. Okay? But this is it, right? This is all that the theorists have come up with so far. So we've done better than 10 to the minus 43 GeV, but still leaves an enormous range of parameters possible for where the dark matter mass would lie. Anything beyond this is a guess, right? We have certain theories, and these theories tell us, oh, maybe this is the dark matter, but we're speculating over so many orders of magnitude that we can't really be convinced that any one particle is the dark matter, right? So one very reasonable guess is that the dark matter may be tied to the standard model scale of about 100 GeV or so. That's one scale in physics, so maybe the dark matter also comes from there. And that's a nice story. It's a story of the weakly interacting massive particle, or the WIMP dark matter. Because if this was indeed the case, there's a reasonable story for how the dark matter achieves its right abundance. That's a beautiful story. It was well worth going after the WIMP. But this experimental program is soon about to hit the solar neutrino floor, right? Beyond which progress may be quite hard. And one has to ask, how do we go past that limit? Right? Since the WIMP is such a good story, how do we go past the solar neutrino floor? So that's one theme of this talk as well. But WIMPs are by no means the only dark matter candidate. If you ask a theorist, it's pretty easy to come up with theories of dark matter. And there are other very sort of generic dark matter candidates out there. Axions, massive vector bosons, and what are called dark blobs, which I will sort of discuss more as we go through this talk. Okay? So given that there's an enormous range of other possibilities, and they could really lie anywhere up here, the question becomes, how do you make progress on this very large parameter space? Okay? How do we actually come up with a program of experiments that can cover a lot of territory instead of just being focused in one part of parameter space? So in this talk, I'll basically talk about how we can search for dark matter all the way from about 10 to the minus 22 eV to roughly about a GeV or so in mass, right? A variety of ideas that cover a lot of territory over there. So here's the outline for the talk. Let me first give you a brief theory overview. So this brief theory overview will mostly cover the very, very light dark matter particles with their mass from about 10 to the minus 22 eV to about 100 gigahertz or so, right? What kind of particles exist there? Why are they interesting? How do you find them? Then let me discuss three possible experiments. One is to search for axions with nuclear magnetic resonance. One to search for what's called a dark photon with a rather fancy radio. Then search for bosons with fancy accelerometers. After that, we'll switch gears for the next half of the talk, where we'll discuss direction of dark matter. This is to help you go past the solar neutrino floor that WIMP experiments are about to hit soon. And I'll discuss a new idea called a magnetic bubble chamber, which is to look for rather light dark matter particles with mass of about, let's say, a milli eV or larger. That work. And then I'll conclude. So let's talk about bosonic dark matter. Okay, how does bosonic dark matter look like? What can we actually use to find it? And before we talk about bosonic dark matter specifically, let's ask a question about photons, bosons that we know and love, and see how we can think about them. So this picture shows photons coming out of some laser, right? And you can think of those photons as individual particles. That's a perfectly sensible way of thinking about them. But an equally sensible way, due to wave-particle duality, is to say, aha, this photon is associated with a classical electromagnetic wave. Okay? This electromagnetic wave has an amplitude E0, which means the photons have an energy density E0 squared. And then this photon is oscillating at a frequency equal to omega, right? And that's what describes the electromagnetic wave coming out of this photon. And one way to find these photons is to measure the time-varying electric field associated with it. You have an antenna, you can drive the antenna. That's one way to find it. So the key point here is that every boson, or really every quantum field, every particle comes with a field associated with it, a classical field, and that classical field will have time dependence. And you could try to detect the particle by going after the time-dependent field. Right? That's the key idea here. So let's look at how that works for dark bosons. So one could ask, how are these bosons produced? What's a typical production mechanism? How do they exist? The idea is the following. If you have something like an axion, it's supposed to be a scalar field, right? So much like how the photon has a classical field associated with it, the axion, for example, will also have a classical field associated with it, okay? And in the very early universe, where the world was created, this field will have some non-zero amplitude, right? There's no reason why the field value has to be zero. In general, we'll have some non-zero amplitude. And this non-zero amplitude will give rise to a non-zero energy density. Much like E0 squared, here is m squared a squared, and that m squared a squared could easily be the dark matter density. Right? So when the universe was created, this field was just existed, and it had some initial density, and that could be the dark matter. Now the crucial difference between a field like the axion and a photon is that the axion has a mass, which means if you look at the classical field that describes it, all of its energy density will basically sit just in the time component here, with there being no momentum. right? So for a photon, because it's massless, energy and momentum are tied together, while for a massive boson, you could basically have zero momentum and have all the oscillations existing solely in time. If you look at this field therefore is dead constant throughout the entire universe, right? There's no spatial dependence at all, and it's just oscillating back and forth. Okay, so it's a constant field throughout the universe, oscillating back and forth. But that's the picture in the early universe, right? When the world was created, so in inflationary cosmology or whatever, this is what would happen. The field gets a uniform value everywhere. We, of course, don't have the privilege of living in the early universe. We live today, right? Today, the field has, of course, fallen into the galaxy. It's developed bumps and wiggles. It's gotten quite random. So even though this is a random field, I can still ask, what is the two-point function of the field? Right? I basically say, this is a random field. The field has one value here. How far do I have to go before the field value changes by order 1? Right? And if you think about that problem in Fourier space for a second, you realize that the correlation length of the field, right? How long you have to go before the field changes by order 1 is inversely proportional to the de Broglie wavelength. Like, it's like e to the I kx, right? That's what allows x to change, the field to change. And k obviously is the de Broglie wavelength. Now for an experiment, you don't just care about the correlation length, you care about the coherence time, which is to say, if the field has one value here, and I'm sitting on the Earth with some instrument trying to measure it, how long do I have to sit and measure it, right? So the coherence time is therefore given by the amount of time it takes for the Earth to traverse a distance that is equal to the correlation length. Now the relative velocity between the Earth and the dark matter is also v, which means that the coherence time will be 1 over mv squared. Okay? And this is what makes this game very interesting, because we know that the velocity of dark matter in the galaxy is about 10 to the minus 3, and for a particle like an axion, we will talk about this in a few minutes, these particles come from high energy physics, okay? They come from QCD, gut physics, whatever. But yet, if you put in the numbers, their masses could be like a megahertz or so. And if the mass is a megahertz, and the velocity of dark matter is about 10 to the minus 3, the coherence time is 1 second. Now, think about what that means, right? 1 second coherence time is nothing in the time scale of the galaxy. The galaxy has been on for 10 billion years. For 10 billion years, everything is totally random, right? But 1 second is very useful for human beings, right? Because we can build a lab-based instrument that can coherently measure a signal for 1 second before it changes to something else, right? So because of this reason, since these coherence times are short enough to be of interest, are long enough to be of interest to human beings, we can think about building instruments that go after this. That's what makes this game possible, okay? And the key idea is that, much like how we will detect photons by building an antenna that measures a time-varying field, we're going to try to detect the time-varying effects of the axion dark matter field, for example. Okay? That's basically what you would do. And you see that there's a natural possibility for resonance in this story, because the coherence time of the field, 1 over mv squared, is basically 1 over v squared, or 1,000,000 times longer than the period, which is 1 over m. Okay? And so you can build some kind of a resonant instrument that's able to amplify your signal to noise, possibly by about a factor of 1,000,000, if you can build a good resonator. So that's the basic idea. You're going to look for the resonant effects of this time-dependent field. What kind of bosons are interesting, right? We naively said, look, these bosons can be from 10 to the minus 22 eV to about 100 eV or so. What kind of crazy theories can the theorists come up with? Theorists can come up with a lot of crazy theories, but a reasonable criterion for what these fields should be is that these fields are so light, their masses are 10 to the minus 10 eV, 10 to the minus 22 eV, so light that you might think that these are interacting bosons. There should be some kind of a symmetry or something, okay, to keep that mass naturally light. So because these, if you think naturalness is a reasonable criterion, okay, we can actually parameterize the ways in which this field can talk to us. And turns out there are only 7 possible ways in which this field can talk to us. And we can actually list all of them. So let's see what the 7 possible ways are. The first, if this is a light boson, maybe it has spin 0, okay? If it has spin 0, the typical example of particles like axions, okay, that's the usual example. And these, pop up in all kinds of theories, which is why theorists are excited about them. But if it's an axion or so, there are only 4 possible ways in which such a particle can couple to the standard model. One is that the field can couple to electromagnetism through this coupling FF dual, F is electromagnetism, or it can couple to QCD through GG dual, that's the gluon field of QCD, that's called the QCD axion. Then it can couple to spins of nuclei through this coupling d mu a n bar gamma mu gamma 5n, or it can couple directly to the Higgs boson through this coupling g phi Higgs squared, and that's called the Higgs portal or the Relaxion coupling. So those are the 4 possible ways in which a light boson can couple to us and still be protected from quantum corrections, which goes mass. If it's a spin 1 boson, the quantum field theory lingo would be that you have to couple to us to an anomaly-free coupling. Okay, that's what it has to be. And that gives you 3 other possible operators. You can couple to, again, spin. So if you have a neutron or a proton or something, then the new dark gauge boson, F prime, because now we think it's a spin 1 particle, so much like the photon is just a massive particle, with the spin 1, it has its own field strength, F prime. So your proton or neutron or whatever can have a dipole moment under this new gauge interaction. Or it can talk to us through what's called kinetic mixing. This is electromagnetism, and this is the new field F prime. So this kinetic mixing operator epsilon F prime. That's one possibility. And finally, standard model particles could be directly charged under this new coupling. And if you want this boson to be naturally light, it has to talk to us in an anomaly-free manner. And the only possible operator then in the standard model would be the B minus L coupling. Okay. And if any of these things are the dark matter, all you will then do is that you put in the fact that the dark matter gives rise to a time-varying field, and that time-varying field will give rise to time-varying effects. And that is something you can go look for. And the frequencies could be anywhere from really about a hertz or about really 10 to the minus 7 hertz, I should fix my slide there, all the way to about gigahertz, because we don't know what the dark matter mass is. It could be anywhere in this broad region. The issue is that current searches are pretty narrow in their frequency coverage. So there's an experiment called ADMX. It's a terrific experiment. It's fantastic. Okay, but ADMX looks for just this one interaction in a narrow range of frequencies of around a gigahertz or so. They're also sensitive to this coupling, but at the same frequency band, right? But as we see, there are 7 possible effects here. We should go after all of them over a much broader range of mass and frequency than we've been doing so far. Now I realize this is a pretty kind of a theory-heavy slide, right? So, so if you kind of lost a little bit of theory, it's fine, because the next slide will make things a lot simpler. Okay, this is just for me to prove to people that I really am a theorist. I'm not talking about. But the key point to go back with here is that there are a limited number of ways in which such a particle can talk to us. So there are 7 possible theory effects, but I claim only 4 possible experiments you could do to go after this stuff. Okay. The question we want to ask is this: look, this dark matter exists everywhere. This dark matter is a field, right? That's it. Ignore all the theory from the previous slide. There's some classical field interacting with us all the time, and that's what we assume the dark matter is. What can this dark matter field actually do? So we're asking, how can a classical field affect the standard model, and so that we can actually go and measure it, right? And here are, I claim, the 4 possible ways in which that can actually happen. So we have a dark matter field. This is an oscillating field, as we said, some A0 cosine MT, something like that. And here are the 4 possible ways it can talk to us. The first thing this field can do is that it can exert forces on electrons and drive currents in a circuit. Right? So this could be an LC oscillator, or it could be some kind of a resonant cavity that gets excited because the dark matter is exerting some force on the electrons. The second thing it can do is that if you have a spin, say a nucleus or an electron, it can make the spin rotate. Right? That's an effect that can happen through a classical field. The third possibility is that if you have a material, right, the dark matter can exert forces on this material. Okay? It can push protons and electrons around and directly move the material back and forth. And finally, it can change the values of fundamental constants like the mass of the electron, the charge of the electron, things of that sort. Right? So these are really the only 4 possible ways in which a classical field can affect the standard model. Okay? And the crucial thing is that, suppose the dark matter did either this or that, right? A very nice way to find both of these effects would be the following. Say the dark matter comes in, it drives a small current in a circuit. The small current will create a small magnetic field, and that magnetic field can be measured with a squid. Say the dark matter comes in and it makes the spins rotate slightly. Each spin, of course, has its own magnetic moment, and that will cause the magnetic field over here to change slightly. And you can again measure that with the squid. Thirdly, suppose the dark matter exerts a direct force on materials that will cause tiny accelerations. That can be measured with an optical or an atom interferometer, much like what LIGO just recently did so successfully. And finally, if it changes the mass of fundamental constants, say the mass of the electron or the charge of the electron, those things will of course affect the fine structure constant, stuff like that, which are of course very nicely measured through optical and atomic clocks, because the clocks use the fact that the electron mass is some number to achieve their actual sensitivity. So the electron mass is changing slightly, the clocks will also wobble back and forth, right? So all of these are sensible experimental ideas, right? Even if you didn't care about all the theory, naturalness, all the stuff that we talked about in the previous slide, if you just restrict yourself experimentally and ask, how can a classical field affect us? This is it, okay? And we're going to talk about experiments that will go after these effects. And what makes these experiments exciting is that you're looking for a time-dependent effect, right? And this effect is going to be in a particular frequency band, right? It's going to occur at the dark matter mass. That's a narrow bandwidth, as we said, about 10 to the minus 6 of the frequency. So hopefully that will help us beat systematic sources of noise, right? Because you're looking for a well-defined signal set by fundamental physics rather than something that you're changing in the laboratory. So let's quickly go over the possible experiments. I'll first start off by discussing what's called CASPER, or the Cosmic Axion Spin Precession Experiment. It's a pretty reasonably well-funded operation now. We got some private funding that started us off, and then now the Germans have really pitched in a pretty serious way, and the experiment is being built at Mainz by Dima Budker, my former colleague who moved there. So here's how CASPER works. Let's say we take a neutron or some kind of nucleon, and that's a spin, right? And so suppose the dark matter talks to us through this operator, d mu a n bar gamma mu gamma phi n. That's one of the operators I talked about earlier. This operator leads to the following effect for the neutron. So if you have the neutron and here's an axion going through the neutron, there's an interaction between the neutron and the axion that is given by this operator, which is equal to this. Okay? The velocity of the axion dotted with the spin of the nucleus, which means that the axion goes through, much like how a magnetic field will cause a spin to precess. This velocity of the axion will cause the spin to precess around it. Okay? That's a spin precession that's induced, going back and forth. So if you want to go beyond present limits, you're basically trying to look for magnetic fields about 100 Tesla or so, oscillating at a frequency equal to the axion mass. If you have a vector field, like one of these hidden photons like things, then again, a similar effect can happen if the dark matter happens to have a dipole moment under this. Much like how if you apply a magnetic field and the neutron has a dipole moment, the magnetic field will cause the neutron to spin. Similarly, the dark matter's magnetic field will cause the neutron to spin to flip if it has a dipole moment under it. The other effect is to look for the QCD axion itself. This is a specific kind of axion distinguished by the fact that it coupled to QCD, so its operator GG dual. This guy solves things like the strong CP problem, if you've heard of it before. But here's how you can look for it. If this effect existed, it turns out that QCD will induce a tiny electric dipole moment for the neutron, and this dipole moment will be aligned along the direction of the nucleon spin, because that's the only vector in town. So how do you find a tiny electric dipole moment? Well, one thing you can do is you can apply some electric field, okay, and that electric field will cause the spin to rotate. That's the basic idea. So what you notice in all these cases is that if you can somehow measure the spin rotation caused by the axion dark matter or the hidden photon dark matter, you're able to detect this dark matter directly. Right? So here's how CASPER then works. We take a block of material, okay, and let's say you align all the spins in one direction, okay, and then you let the axion do its thing, either because we apply an external electric field for the electric dipole moment effect, or there is the wind of the axion, as we call it, the velocity of the axion that flows through this. In either case, if the axion was a dark matter, the spins will start precessing, right? As the spins precess, the magnetization of the sample will change, and you can stick a squid in here, which will then measure that small change in the sample magnetization. Now, there's a natural possibility of a resonance here, if you are familiar with NMR. If you apply an external magnetic field, there's something called the Langmuir precession frequency, which is the frequency at which the spins like to precess naturally. Okay? And when that precession frequency equals the mass of the axion, there is a resonance where there will be an enhanced spin precession. Okay? Of course, we don't know the mass of the axion, so we don't actually know where we will tune this thing to. So the way this experiment will work is that we will pick one value of the magnetic field, and you will see, if you get a spin precession or not. If it doesn't work, you will change the value of the magnetic field. So now you have set a different Langmuir precession frequency, and you see there's one point where you get a big spin precession. And if you found one place where there's a big spin precession, and you're a theorist, you will declare that you found the axion, but if you're an experimentalist, you'll go and find the noise source that caused it. Right? So you'll keep trying until hopefully you actually succeed.
So what are the main sources of noise you can pick up?
So here, certainly EMI, right? Like if there's some magnetic field coming in, that's the dominant one, yeah. Also, you can also have like vibrations, because you'll have, there's a big B field, there's a squid sitting out there. You want to make sure that there are not too many vibrations coupling those two things together. And it's a frequency-dependent statement because basically, as you go to lower and lower frequencies, these vibrations become more problematic. At higher frequencies, there can be more efficient resonance.
How fine should be your step then?
Oh, 1 part in a million. Yeah. So, and we fold that into our sensitivity on how we actually get there, right? This is true for pretty much any axion experiment. So, for example, if you're looking for this general coupling of axions to any nuclear or electron dipole moment, in this case, it's just the nucleon that we talk about, and that's the fact that the velocity of the axion will cause the spins to precess. Here's how well we think we can do if everything goes to plan. So this is the coupling, this is where current bounds are, okay? And this is the purple line where the QCD axion sits. It's a specific axion that you might want to look for. ADMS is searching for them over here, and we think we can cover all of this territory out here. Okay, so we don't quite get to the QCD axion. We are kind of limited by a fundamental source of noise, the magnetization noise, which you can only damp by making the thing bigger and bigger. But we can get a bunch of territory out here. Okay. And we basically assume when we draw the sensitivity curve that we spend about 1 year scanning a full decade of frequency. So 1 megahertz or 10 megahertz is 1 year with this step size. For the QCD axion itself, you want to go after the time-varying electric dipole moment, and this is again the time-varying electric dipole moment operator out here. These are current limits in astrophysics dominantly, and this is the QCD axion living out here. And if you look at it, everywhere where this red line intersects and goes below this purple line, we're sensitive to QCD axion dark matter. So we're dominantly sensitive to axions with a mass below about a megahertz or so, okay, corresponding to axion decay constants at the gut scale or larger Planck scale, that order. And ADMS is somewhere here. So we are basically sensitive to a pretty complementary range of axion mass and frequency, more to the sort of what are called string axions. Like that's kind of the things that are not dominantly sensitive. Let me now discuss this.
Do you need to cool your sample?
Cool our sample. So, yes. For the EDM experiment, we do have to cool them. Okay, to like below Kelvin, doesn't have to be millikelvin, but like 100 millikelvin, something like that. But for the spin precession experiment, which is just sort of simply looking for the velocity of the axion, there essentially we can, I think, do it at 77 Kelvin, like at sort of liquid xenon, because that's exactly what we're trying to use right now. So let's talk about this experiment, dark photon detection with the radio. This is being built by Kent Irwin at Stanford, and as of this morning, funded by the Heisman-Simons Foundation. But we also got some cash from Slack and Kaipak to build some small Pathfinder versions. So here's how this idea works. What's a dark photon? It's a very simple thing. A dark photon is a photon with a mass. Okay, so this is the photon, the Lagrangian electromagnetism. Okay, F, and this is a dark photon F prime. Your electron couples to both the regular photon and the hidden photon, the dark photon, the A prime. Okay, well the A prime has a mass. That's a big difference. Okay, so the way you want to think about finding this experiment, finding this kind of dark matter, is that you have a photon with a small mass, okay, and small coupling to all charged particles. How do you actually find it? So the basic idea is that if this is the dark matter, right, the hidden photon is the dark matter, there will be a hidden electric field everywhere in space, oscillating back and forth. And this hidden electric field can drive currents behind electromagnetic shields. Okay, so that's the basic idea. So you have a shield, there's a hidden photon, that's dark matter. What will happen is that the regular electromagnetism will hopefully get blocked by the shield, while the hidden photons will go in. Inside that, you stick a fancy resonator, like an LC oscillator, okay? And you hope that the hidden photon will come in and excite the LC oscillator. Now, of course, we don't quite know what the dark matter mass is, right? So we have to have a tunable LC oscillator, a radio, if you will, and you just keep tuning it till hopefully you find the place where there's a big signal, and we call this experiment DM radio for that purpose. And this is basically where DM radio thinks we think we can go. This is in coupling, epsilon, and mass. And as you can see, we can actually cover a lot of territory beyond present bounds of this over a pretty broad range of mass. Okay, and here are the parameters that we assume in making this model. Again,
there's a time circuit that you
yeah. Well, so the frequencies could be anywhere from about a kilohertz to about a gigahertz. Finally, let's talk about how to detect dark matter with accelerometers, the final idea that I mentioned.
Actually, so is there like a relative abundance line anywhere on that?
It's a question of how you produce it, right? So all of this is produced essentially non-thermally.
Okay, so you're just saying that it's there somehow. And then
Yeah, so you
find it first, and then you figure out how.
so for example, with inflation, you can very naturally make it all of dark matter.
Also, we survive it then.
Exactly. Yeah. Yeah, I mean, like, these things can't be thermal in a sense, they're too light, right? So they would have to be non-complex. Let's now look at what's called B minus L dark matter. That's this thing I talked about. The B minus is a very simple theory. There is a, some kinetic term, there's a mass term, and there's a coupling between standard model particles and the B minus L gauge boson, just like electromagnetism. The thing about B minus L is that under B minus L, protons, neutrons, electrons, and neutrinos are all charged. In electromagnetism, obviously, only protons and electrons are charged. These two guys are neutral. But in the B minus L, everything is charged. And this has the feature that if you take an electrically neutral atom, the electrically neutral atom will be charged under B minus L. So if you bring two electrically neutral atoms together, there will be an extra force between them. Okay? And that force has been looked for in many experiments, and current bounds constrain them to be smaller than about 10 to the minus 21 or so, this coupling. But we think we can do better if this is the dark matter and search for these deeper territory. The basic idea is the following, is that if the B minus L gauge boson is the dark matter, right, then there's an oscillating electric field, B minus L electric field associated with this, and that can accelerate neutral atoms because neutral atoms have a charge that's unscreened because neutrons have a non-zero charge at the B minus L. And this force, of course, depends upon the net neutron number, right, of the system, and hence it will violate the equivalence principle, right, because different materials will feel different accelerations depending upon the number of neutrons that they have in the thing, because a neutron is a charge of the system. So essentially, in this case, you can think of the dark matter as directly exerting a time-dependent equivalence principle violating force on matter. There's another theory called the Relaxion. I like this theory, it's my own theory. This theory has the feature that's able to solve the hierarchy problem through cosmic evolution. I won't talk about it today, but one can generically ask if this happens to be the case, how would we actually find it? Okay, and this again is part of the general operator analysis I talked about earlier, where we talk about some field that is coupled to the Higgs through this operator G phi Higgs squared, the Higgs portal, as it is. Okay, so what can happen in that case is that once the Higgs acquires a Vev and gives masses to fundamental particles, the Relaxion itself will mix with the mass of fundamental particles, and now if it's a dark matter, it's going to give rise to time-dependent variations in the masses of fundamental particles. Okay, as this field oscillates, the mass of quarks and electrons will change slightly. Okay. Furthermore, the dark matter has a velocity today, which means that when this field is sitting there, because of the velocity, there's a gradient appearing in there, and that gradient is going to give rise to forces on atoms that are proportional to the velocity of the dark matter. Okay. And again, this is a force that the dark matter is exerting through the Higgs boson. The Higgs boson doesn't know anything about gravity, so this force will also typically violate the equivalence principle. So once again, if this is the dark matter, you're now going to get a time-dependent violation of the equivalence principle on your system. So how do you find such a thing? Here's the basic idea, right? We can actually make use of all the wonderful work that's been done in testing for the equivalence principle, in testing for violations of the equivalence principle by a number of groups around the world. So here are two possibilities. So one is to make use of what's called a torsion balance that the people at the University of Washington have been building for many years, and it's a very nice idea. So basically, their concept is that you take two isotopes or two different materials, titanium and beryllium, and here's what you do. If the dark matter is out there and it's exerting this time-dependent equivalence principle violating force, it will exert a different force on titanium and a different force on beryllium, sorry, a different acceleration titanium and a different acceleration beryllium, which will then cause this torsion balance to rotate slightly. Okay? And as the torsion balance rotates slightly, you can measure that angle with an optical interferometer. That's one way to find it.
Could you clarify why it is different? Why it would be different?
So if you say the B minus L, right, then the charge depends upon the number of neutrons in titanium versus the number of neutrons in beryllium. Those are of course different, which means the acceleration will be different. And if it goes to the Higgs boson, then basically the Higgs boson doesn't, the equivalence principle is a very special thing about gravity, right? So it's easy to break it, essentially. So depending upon details of this thing, it's easy to have. Secondly, you can use an atom interferometer. So at Stanford, for example, there's an experiment where they're basically trying to do Galileo's experiment again, which is that they take two different clouds of atoms, rubidium-85 and rubidium-87, and they drop them, and they try to see one of them is falling faster than the other, okay? Because they have a very precise way to measure the acceleration. And so again, if you find one of them falling faster than the other, naively you think you're violating the equivalence principle, right? Now there's an important advantage to going after the dark matter signal in these experiments, okay, which will actually allow us to go well beyond present limits on these cases, because what limits these experiments currently is not measurement sensitivity. It's not their ability to measure a small angle or their ability to measure a small acceleration. One of their dominant systematic problems is that if you try to do any of these experiments on the ground, you have to deal with the gravity gradient of the Earth. So for example, take this experiment, right? Where you're trying to take rubidium-85 and rubidium-87 and you drop them and you try to see one of them falls faster than the other. Now of course, if you drop rubidium-85 slightly above rubidium-87, they will in fact fall differently. You've not then discovered the violation of the equivalence principle. You've just discovered the fact that the Earth is a sphere. So there's a slightly different gravitational potential, a little bit above the other. Okay, and that's a major systematic for these experiments. However, when this is a time-dependent effect, there's a nice way to ignore this problem. Basically, because the signal from the dark matter is oscillating in time. So let's say the signal oscillates at a frequency of 1 Hertz or so. So then you will find that rubidium-85 falls faster than 87 for 1 second and then changes again, right? And that can't be mocked up by a static spherical Earth. Okay, it can only come from time-dependent effects on the Earth, which are substantially smaller, allowing us to go deeper in this parameter space. One can also use pulsar timing arrays to go after this effect at very, very low frequency. Pulsars are basically wonderful stable clocks. They're presently being used. These pulsar timing arrays are being built to search for low frequency, 100 nanohertz gravitational waves. Okay, and the idea is basically that if there's a gravitational wave going between the Earth and the pulsar, then the signal from the pulsar will get modulated because there's stretching and squeezing in space, and that's something they can actually measure. What will happen in this case is that, say, if it's a B minus L or this Relaxion particle that's exerting forces now between the Earth and the pulsar. Of course, the pulsar is a very different beast than the Earth, so there's a very big equivalence principle violating effect between the forces of dark matter on the Earth versus the pulsar. And again, that force leads to relative acceleration, which will also modulate the signal. And that's something one can actually measure. Finally, if you're looking at something like the Relaxion, then the Relaxion will change the mass of the electron itself at the location of the Earth. And these comparisons ultimately happen because you're using an atomic clock on the Earth to time your arrivals. So the electron mass changes, your comparison will change. That's again something you can directly measure. So we can again go well beyond present limits on these particles. Advanced LIGO is able to go pretty easily. They're not even particularly optimized to do this. They're just a phenomenal experiment, obviously. But if you build a more dedicated setup, you can go well past current bounds on these particles. Let me quickly flash what you can do for the Relaxion as well out here. And let me give you like a bonus, okay? If you manage to build these experiments, what else can you actually do? So this is something that I've been puzzling about recently, and it's got me pretty excited, is that all of our dark matter experiments are based on an assumption that the dark matter is some particle spread all around the universe as individual particles, right? That's how we think about it. And that picture is true if the dark matter happens to have weak self-interactions with itself, okay? Now we know the standard model, we know that the dark matter and the standard model don't interact very much, right? But the dark matter could easily have pretty strong self-interactions with itself. These are not that constrained. Now imagine the dark matter actually had these reasonably strong self-interactions with itself. In that case, it won't really live in the galaxy as individual particles floating around. It will tend to coalesce and form big lumps, just like you and I, right? We are not individual particles, we're all lumped into rather massive objects compared to fundamental physics. So if this happens to be the case, the dark matter will be like a little rock or something floating around, right? And it's hard to find these guys, obviously, because there'll be very low number density of them, right? Because it's not, the mass could be enormous. It will be like 10 to the 8 grams, right? All this lump sitting together, okay? So how do you find something that is that heavy when the number density is so low? So this is a bit of a wild shot, if it works or not, right? Because typically you need something like a planet-sized detector to be able to have any hope of seeing it, okay? But it is possible, it doesn't have to be the case, but it's possible that if the dark matter is one of these lumps, it may also source these long-range classical fields. So the dark matter is interacting with us through something, we assume, and that interaction may well be because of some classical field that it's creating, like a B minus L field or a hidden photon field, whatever it is. So that is the case.
These like self-interactions, it's like sort of one-ish, like the limit on strong interacting dark matter is like one-ish scattering the whole time, right?
Per GeV in mass.
For GeV, okay. So you're, okay.
Yeah, so if you take that number and let's say you put it on the early universe, like well before galaxies, etc. formed, you can easily form these big lumps. In which case, those bounds dramatically disappear.
And that's, okay.
Yeah. So how do you find something like this, right? You know, it's a crazy thing, but let's see if we can do this. Now, here is kind of and which is why I say this is more like a bonus. You wouldn't necessarily go around trying to look for it, but if you build these kinds of detectors that I talked about in the slides earlier, this is the kind of thing you could easily do. Because imagine you actually have a bunch of these experiments around the world, right? Like, you know, CASPER, DM radio, one of these things, and you build a few of them, okay? A couple of them here and there. They're not terribly expensive. So this lump may just go through the Earth once, right? Okay. What you'll find is that this will create some big classical field that's just going and exciting detectors at the same time. Okay. So the effects of these classical fields on your detectors is exactly what we just talked about earlier. It could create a current, it can cause spin precession, acceleration, vary some fundamental constants, so on and so forth. Except this effect will not be your oscillating signal at a well-defined frequency, right? It's just like one shot. It just goes through, creates like a delta function of time, basically. So if any one experiment saw it, you would just think, oh, it was just some noise locally, right? Someone, you know, stepped on the switch or something like that. But you could then, if you had a network, if you had a couple of these experiments, you could do a cross correlation, right? And then see if you saw the same signal here and here at the same time, stuff like that. That allows you, if you had a network, to basically probe these big lumps. Okay? So I think this is kind of a bonus, right? It's quick. One doesn't have to do anything dedicated for it. If you have these experiments already, it's just a different way of doing data analysis.
If this sort of dark matter existed, wouldn't we see it not forming halos or see some sort of interactions like a little cluster where things?
Yeah, so this is what Lee was asking, but basically those bounds are rather weak.
Yeah.
So essentially, you know, let's say the classical field range is like 1,000 kilometers,
Yeah.
which is roughly what you would need for the Earth. For the Earth, it's interesting. Cosmically, it doesn't do anything.
Yeah.
So the remaining few minutes, let me see how much of the remaining part I can actually cover. We talked about a bunch of this stuff out here already, right? All these bosonic fields that cover a lot of territory. Let me now switch to asking, can we do beyond? Can we do sort of probe WIMPs beyond the solar neutrino floor? Right? There's the right way to find WIMPs, obviously, through hard scattering, and pretty soon they're going to hit solar neutrino floor. How do you go beyond it? And then and if you notice so far in the discussion, we've talked about particles with a mass of about 10 to the minus 22 eV to about 10 to the minus 4 eV, this huge range. Okay, and this is possible basically because these experiments are leveraging the following fact: the dark matter here is very light; it has very small mass, right? So we're not trying to find this dark matter by making it scatter and deposit some small amount of energy. That's very hard to actually find. Right? Unlike the WIMP or something where you get tens of keV, this is very small amounts of energy. So what we used to find the dark matter here is that we made use of the fact that the dark matter is coherent for a long time, right? The coherence time of dark matter was 1 over md squared. So as the mass went down, the coherence time was long. So at this high frequency, it was something like a microsecond. At a megahertz, it was 1 second. All the way down here is about a million years. That means you had a long time to study the signal, and that's what we actually leveraged to be able to see this. So in a fancy way, you would say, I had enough time to build a phase in a phase experiment, like an interferometer, to actually see it. But as you go to this higher frequency range, right, about 10 to the minus 4 eV or so, the signal is not very coherent for too long. So it's hard to build phase to see it. At the same time, the energy being deposited is too small to be able to see it in conventional dark matter experiments, right? So what would you have to do to go after those two things? And that will make up the remaining part of my talk. So let's quickly talk about directional detection, how we think it can actually work. So here's the problem we want to solve. If you look at a typical WIMP dark matter experiment, right, then here's the issue, right? I have some detector, right? And the problem is that neutrinos from the sun, for example, and dark matter, they look very similar in the way they scatter. They come and scatter in the detector, they deposit some energy, knock off some nucleus or whatever, and that's exactly what you're measuring, and they look identical. Right? They interact once in the experiment, unlike your typical radioactive background, which will scatter more than once. Now, the problem is we know there's a sun next to us. The sun produces a bunch of neutrinos, and that's an irreducible background that we will hit soon. So what we can make use of is that the sun, we know where it comes from, what direction it comes from. So somehow you're able to measure the direction of the nuclear recoil, right? We can veto all the events that come from the side of the sun. Well, the dark matter should be isotropic, so we can look at the part where the sun does not exist, and therefore we will be able to just veto those events and go after the dark matter. That's the basic idea. The challenge in this game, obviously, is that these cross sections that you need are super small, right? So you need a big target mass detector to be able to go after it. Otherwise, you won't even have any events to find. So the difficulty is really that you need directional detection at roughly solid state density in order to be in the game, to be able to do something useful. So how could something like that actually work? Okay. So let's look at what we can actually look for. What is the signal that you might even search for? Okay. So dark matter or neutrino comes in, it scatters off the lattice of some detector that you have, deposits some energy. Okay. What does that nucleus do once it's been kicked that way? Well, that nucleus will go and click other things. Okay. And it will create a damaged cluster in that area. Okay. Basically, if you think about it, you deposit something like tens of keV of energy, and the lattice potentials of these systems are something like tens of eV, which means this guy can go around and do a bunch of damage. Okay, so there's a damage cluster created by the dark matter hitting in and destroying the lattice locally. The difficulty, of course, is that this damage cluster, while it's well correlated with the direction of the initial ion, is all localized within something like 50 nanometers. It doesn't go too long, right? So it's like I've taken a bullet, I shot in the dark matter in my experiment, and there's a tiny track, 50 nanometers long, that is telling you what the initial direction was. Okay? So the challenge will basically be, how do you actually find this small damage cluster, right? So let's look at the signal itself. Okay, so if you run something like a trim simulation, and we put in like ions from about 10 to 30 keV just to see what actually happens, you notice that you create something about 200 to 300 vacancies and interstitials. That's the lattice damage that you're creating, and it's pretty well correlated with the direction of the initial ion. Okay, if you could actually measure it, then you're in business. But the challenge, obviously, is that you need to be able to do some kind of nanoscale measurement to be able to look at this damage cascade. Okay, and your detector is like a ton-sized big. That's a huge detector. How do you actually accomplish such a goal?
So can we go back to
Yeah.
to the previous slide?
Yeah.
So you said about 200, 300 vacancies, and these are
long-lived vacancies. Yes.
Vacancies. So
Yes.
that means that, for example, for some of us use photon detectors, these are lost energy.
Yeah.
So we should clearly see that our, like, for example, our ionization yield, because this is like for 1 keV is going to be for let's say 10 keV is 1.5 keV lost.
Right. Yeah. Exactly. Yeah. It's sort of basically dumped into this precisely. Yeah. So yeah.
It should be in our data. What I'm saying.
Yeah. I mean, like this is pretty small, right? If you think about it, at like 10 keV initial energy I deposited, I only get about say 300 vacancies or so.
So that's 30 EV, so it's 1 keV.
1 keV roughly. Yeah.
It's 10%.
Yeah.
If you do absolute full
Yeah.
integration.
Yeah.
We should be able to tell whether it's coming.
Yeah. I mean, if trim is right or not, absolutely. Yeah. So how do you find such a thing, right? This is actually true, right? I mean, how do you find such a thing? So here's where the technology of NV centers or nitrogen vacancy centers and diamond becomes really interesting. So here's what happens. Okay, if you take diamond, and it's a nice carbon lattice, and what you do is you replace some of the carbon atoms with nitrogen, and there's a vacancy next to it. So there's no carbon sitting there. Okay? That's what the system is. If you remember your chemistry, you will realize that once there's a nitrogen sitting like that, there's an electron sitting over there, an unpaired electron. And the whole point about NV center, the nitrogen vacancy center physics, is that you can study the energy levels of that electron by shining a laser beam at it. So you shine some laser beam at it, you ask this electron to undergo transitions, it'll then go up and down and decay, for example, and the light from that can be collected through a lens, and you can actually figure out the spectroscopy of this NV center. And that can be done now. And these electronic levels are basically sensitive to crystal environments of the order of 50 nanometers or so. And experimentally, okay, they have demonstrated a density of NV centers of 1 per 30 nanometer cube, okay, in like a bulk diamond sample. So these bulk diamonds are about a millimeter or so. That's what they've needed so far for the experiment. They have not built like a meter cube of diamond, right, obviously. But at least, the technology exists to create these sort of high density sample at like solid state densities. That's actually existing. And people have experimentally demonstrated these nanoscale measurements, right, where basically these NV centers have been used to probe the local chemical environment of these systems at the nanoscale. And many groups in the world are doing this, largely inspired by issues like quantum computing. But that's what the technology has been built for, and we can see what we can do. And there's a natural question now. We have a nanoscale signal, okay, from the dark matter, and we have a nanoscale sensor. Can be done? Can you actually put them together to try to do something? What would this experiment sort of look like? And you might be skeptical and say, look, diamond, you need a meter cube of diamond. Even if you convince a DOE to give you a meter cube of diamond, you may take the money and disappear in the Bahamas. It's a very reasonable thing to do. But like this phenomenology is true not just for diamond, it's also true for what I call F centers, Faber centers, or metal halides, and a bunch of other things. Right? There's a bunch of crystals where the same phenomenology exists, where there's a vacancy paired to some defect, and that can be studied very well. The diamond is just the most studied of these examples. All right, so what's the physics, right? One can ask that question irrespective of the experimental thing. So let's see what actually happens here. So I've got my dark matter coming in. It's created a bunch of strain in the crystal. It's created a bunch of damage in the crystal by knocking things around. Okay, and what will happen is that this crystal has now gotten disordered locally, and that disorder will create strain. Right, atoms are not where they're supposed to be, and that strain will shift the transition lines of these electrons. That's what will happen. So you can go ahead and see how that can be calculated. This is from a paper from 1928 when people did these things more carefully. So this is a strain from each defect that drops off as 1 over r cubed, it turns out. It's an application of Hooke's law. And you get to take that and multiply that by something like 100 to 300. That's the number of vacancies that you created. And then you can sort of look at your trim simulation that we did and ask if I have these, if I have a 10 keV ion going in, creates a bunch of damage. How much does that damage shift the strain field in the system, and couple that with the transition energy shifts, and ask what is the frequency shift you get, right? Because that's what you have to try to measure, frequency shift at the ND center. And you basically find that the ND center shift at something like 30 nanometers is something like about 100 kilohertz or so, while the natural line width of these systems is about 1 kilohertz. So locally, right, within this 50 nanometer region that you're talking about, your signal to noise is a factor of 100 to 1. Right? That's not too surprising because you created something like 100 to 200 lattice vacancies and distortions in that region, while your ambient density of ND centers was only like 1 per 50 nanometer cube. So locally you have this big signal, okay? Except this big signal is now in your massive detector, right? That's what you have to find. But it's interesting that the single ND center itself has a sensitivity to find this cascade. So here's the detector idea, right? How do you think to do something like this? It's a very cartoon concept, okay? So what you want is to get a large detector, obviously. That's the way you'll be in business. So you take some large detector where essentially you'll have these big segments, okay, which have a large area, but thickness of about 1 millimeter or so. We will come to why we need 1 millimeter thickness shortly. But roughly, let's start with that. So you basically take your detector, it's segmented, it's got these sections, each of them like big area, but 1 millimeter in thickness. You using standard techniques, you create an ND center density to start with of 1 per 30 nanometer cube, okay? And then you use conventional WIMP ideas. People know how to do this very well, collect scattering light, ionization, etc., to look at what are the events that are interesting, right? There'll be a few events that are actually from WIMP dark matter, hopefully, or from neutrinos. Most of the events you can reject using very standard things. They'll scatter more than once, etc., etc. So you use the standard WIMP ideas to reject most of your background and focus on the few events that you think could be either from dark matter or from neutrinos. And only for those few events do you actually have to find the direction, right? That's the problem we're trying to solve. So we have to study these few events per year to detect whether it's dark matter or a WIMP. Okay. So here's how we hope to do it, is that, the conventional sort of WIMP ideas, you roughly know the location of this thing to about 1 millimeter or so. Okay? So then you say, aha, there's something interesting happened there, something interesting happened there, and let's now pull those sections out and sort of subject them to further study. Okay? And the further study is that you will then shine light on these systems and then do the ND center spectroscopy to know what the line shifts actually were. Okay? Now, with this naive ND center business where you just shine light on the system, you can effectively localize the damage to within a micron or so, because that's the light wavelength, right? So by just shining light, you won't be able to do localization better than a micron, because that's the wavelength. So how do you go to the nanoscale over here? And this is really the reason why we had to segment the detector, right? Is basically if you want to get nanoscale resolution, the way this is done in these experiments is that you apply a big magnetic field gradient. And this magnetic field gradient will obviously cause an intrinsic shift to your frequencies, okay? And you can therefore use that to get sub-micron resolution. And that's basically how they do the nanoscale resolution for these ND centers. And that's the reason why we had to segment the detector, because we just can't study it purely optically. We have to apply a magnetic field gradient to know exactly where something interesting is happening. Okay. So let me give you a quick results of where we think we can do. This is what we did. We took a crystal, put a grid of NV centers, density is 1 per 30 nanometer cube. We sort of ran about 1,000 trim simulations, get a cascade for each, and then you can ask, can this grid distinguish the direction and tell you head versus tail, things of that sort, right? This is all just some simulation. We haven't built a detector or any of this. Let me sort of quickly get to the punchline. Essentially, we can make use of the fact that there is most of these, damaged clusters. When you study them, you realize there is more damage in the tail of the cluster than the head, and so you can use that asymmetry basically to tell head versus tail discrimination. And we think we can get like efficiencies of something like 70 to 80% with a pretty small false positive rate. Okay, 4% or so these experiments, which mean that even with like a few events, you should be able to do 5 sigma detections.
So what's the dark matter mass?
Typical with 100 GeV.
That's out of the solar.
Yeah, exactly. Then you get into the atmosphere.
The atmosphere regime.
No, this is like 10 to 100, like 10 GeV. So yeah, this doesn't work for like light dark matter below 5 GeV or so, right?
Yeah.
So this is like 5 to 50, that order.
But for if dark matter gets too heavy, you get the directionality of the atmosphere.
That's true. That's true. That's right. Yeah. So this is like I would say, yeah. I mean 5 to 50 GeV. That one. Finally, let me discuss this magnetic bubble chamber. I guess I'll go a little bit over time, 5 minutes possibly. Sorry about that. I tend to talk too much. So let's see how we can actually do that story here. This is the, can we cover dark matter mass in this region 10 to the minus 4 eV to below a GeV, that region. And the problem here is that the coherence time of the signal is too short to use all these techniques on this side, and the energy deposited is too small to typically use conventional WIMP ideas. And there are many interesting ideas out here. I by no means claim that I'm going to cover all of this or whatever. I'm just exploring some part of the territory in this region, okay, closer to over here, 10 to the minus 4 eV. And one way to think about this might be that maybe you need an amplifier, okay, that can amplify the small amount of energy being deposited. That would be a good thing in this story. And the crucial thing, of course, is that you typically need a large target mass. You will try to find dark matter. You have a rare dark matter event, and usually that requires an amplifier that's stable for a long period of time, right? If you build an amplifier and for some engineering purpose, and the amplifier is stable for an hour, it's probably good for most real-world applications. But for dark matter, that's not good, right? Because the amplifier will, that will limit your thing. So here's an idea of how such a thing might work. So let's take a system, right? And let's say it's like a magnet. It's got all these spins all aligned in one direction, okay? And let me now apply a magnetic field in the opposite direction, which means each of these spins is now in some excited state, okay? Excited state is a Zeeman energy, G mu B, the standard thing. And let's say the following thing happens. Maybe the dark matter comes in, it scatters, it deposits some heat, and let's say that heat causes those spins to flip, okay? Just makes them jump down. So as the spins flip, okay, since these spins are in a metastable state, they will release some extra energy, okay? And maybe that extra energy will cause more heating, which can cause nearby spins to also flip, okay? So you might hope that in such a system, right, you create what's called a deflagration, or basically, or a spin burning, if you will, where you start with all the spins aligned like this, you apply a magnetic field in the opposite direction, the dark matter comes, it scatters, deposits some heat, that causes nearby spins to also flip, and you've now generated a spin wave in the system, right, where all the spins start flipping, amplifying the initial energy being deposited, much like a bubble chamber. And you can ask, is this crazy thing possible? Is something like this even existing? Right? And how stable is such a concept? So that brings us to the nice topic of single molecular magnets, right? So let's first talk about a ferromagnet, where one could try to do something very similar, where all these spins are indeed are aligned together. I apply a magnetic field in the opposite direction. What's going to really happen? So can I cause a few spin flips to make everything else flip as well? In a ferromagnet, this does not occur because spins are too strongly interacting with each other. The spin-spin coupling is strong, so one guy flips. He doesn't want to make he doesn't really want to make everyone flip together. Okay, he'll sort of come back to where he used to be. Okay, so you need like a weak spin-spin coupling so that each spin is individually able to relax. Okay, without dragging everybody together. Okay. On the other hand, what you want to do is to say when the spins relax, you still have to take the heat from that spin relaxation to the guy nearby, because it's the heat that's going to cause that guy to also relax. Okay? So you need a system where there is a large heat conduction, even though the spin-spin coupling is weak. Okay? Then you could try to find this phenomenon. And that brings what I call these organometallo complexes, okay, some chemistry stuff. Never thought I'd be learning chemistry again. So here's how they basically work. You have a central metal complex. Okay, this could be manganese or iron, something like this. There's a huge metal spin sitting there. And what happens is that this thing is now surrounded by organic material. Okay, this could be like an acetate or alcohol or various other systems sitting around it. And what the acetate or the alcohol is basically doing is that it sort of spatially separates one spin from the next spin. So since there's a spatial separation, there is a weak spin-spin coupling now. Okay. However, the acetate, etc., provides heat conduction. Right? There's still material that allows you to take heat from one location to the next one. So you can still get large densities and stuff like this. And hence the term single molecular magnet, because each molecule more or less behaves like an independent magnet because the spin-spin coupling is weak. Okay. These are recently discovered in the early 2000s or so, and people know like about I think 800 examples of these things. Okay, so in chemistry this is a new toy. People sort of love to play with, and they can indeed make rather large samples of these guys. And this crazy phenomenon of what's called magnetic deflagration, where you deposit some initial heat and the heat causes the full spins to flip, has been experimentally demonstrated in manganese acetate complexes, basically. So let me quickly tell you the physics behind this. It's a pretty simple Hamiltonian that sort of describes the system. It's basically a two-level system with some barrier. Okay, so when there's no external magnetic field, there are obviously two stable states, right? Spin up and spin down. They are both degenerate. You apply a magnetic field, one of them will go above the other, and this guy now is in a metastable state. He wants to relax to the ground state, but there's this barrier that he has to penetrate through to get there. That's what makes that relaxation slow, because it is a quantum tunneling process. If you look at the lifetime, there's some initial intrinsic relaxation time that's exponentially suppressed at low temperature. Okay, and thus you can see that at low temperature, you can easily get an extra very, very long-lived state. But you realize that if you dump some heat locally, the heat can increase the temperature quickly enough that this exponential suppression goes away, causing this relaxation to exist rather rapidly. So when will this relaxation actually occur? When do you actually get this deflagration? So here's a question you want to ask. You say, I'm going to take my sample, I'm going to take a size of lambda, okay, and heat it to some temperature T, and now I have to ask, will this heat actually cause spin relaxation or not? There are two possibilities. If you take this region of size lambda and heat it up to temperature T, the heat can diffuse away. The thermal diffusion will lower the temperature. Or within that time, the spins can flip, release energy, and increase temperature. If this occurs before that, then all the spins will relax. If that occurs before this, then the heat is just lost. Okay? And the crucial point is that the thermal diffusion timescale depends upon lambda squared. But lambda is the initial size of the region that you made hot, right? Because this is some random walk that takes the heat away from that system. And if you have a random walk, it scales to the size of the system. The bigger it is, the slower the heat will dissipate out. It takes a lot longer to cook turkey, for example, right? While the thermal relaxation time over here is independent of the size of lambda, right? This is some intrinsic quantum process. So basically, if you take any system and you make it hot enough for a big enough region of space, this flipping will occur, right? At some point, this inequality will be satisfied. The question is, can you actually do that for interesting ranges that you care about? Okay. Effectively, if you think about this kind of detector, these parameters, like the thermal diffusion timescale, this obviously a material-dependent property, this relaxation timescale, and this barrier, these are parameters of the system that basically choose how much heat you have to initially deposit so that you heat up a big enough region, causing the spin flip to occur. Okay? And in principle, you can go to pretty low thresholds. There are examples where this relaxation time is as small as 10 to the minus 13 seconds, with barriers as small as 70 Kelvin, and you could in principle do something like 10 milli-eV or so. Okay? I'm sort of way over time, so I'm not going to really go through the details of this. You can talk to me in person if you care. I'm happy to tell you more. But with that, let me actually conclude. Pardon?
From outside.
Oh, from outside, okay. All right. So my motivating factor of the last several years has been that we have really poor observational constraints of dark matter, right? There's a huge game out here, and I think it's like really important that we think of ways to pretty much cover as much of this parameter space as possible, because the last 30 years or so, we've been very, very focused on one set of ideas, right? And that was, of course, an investment worth doing, because the WIMP was indeed very well motivated, but I think now we're at the time when we should open our minds and try to cover as much as possible. Thank you. Yeah.
You mentioned the possibility of blobs of dark matter, and I'm wondering, is Is anyone searching through LIGO data?
Yeah, actually, there are people trying to do this. Yes. So for absolutely, yeah.
Do you know what sorts of signatures? They must be different from what they see.
Yeah. So they're sort of like transients, right? So essentially, you're seeing the delta functions kind of thing. Yeah.
So what's the density of these blobs? I guess what would you so if they're strongly interacting, they're probably something like an isothermal, like each blob.
Yeah.
Might have like an isothermal density profile or something, right? I mean, I guess this is hard to estimate.
I mean, in a sense, like you know, as far as the physics of the galaxy today is concerned, these blobs will behave just like regular dark matter.
But like, okay, so I guess two questions. Like, well, one, I guess, okay, so what is like the density? What would be like the density of these blobs in the galaxy? Like,
Yeah, it should be, because the thing is, the way you might think that these things would form is that like there's some asymmetric sector or something like this, where there's a strong coupling scale, so these things coalesce, etc., etc. There's a freeze-out process. Everything occurs in the early universe. After that, they're just cooling and behave exactly like dark matter.
So like the characteristic mass of a blob
would be set by the strong coupling scale of that sector, so you could easily make it, you know, in a sense, you know, there's a lot of free parameters out there. So it's not too hard to get 10 to the 20 GeV or 10 to the 25.
Okay, I guess I'm trying to drive it into the gravitational lens overshoot. Is it possible to?
It is hard to get to that extreme, yes.
Okay.
So if you look at the masses, they're talking about more like 10 to the 8 grams or something like that. So they're not, you know, big enough to make it into that regime. Yeah, exactly. Yeah.
So your directional dark matter, the diagonal one.
Yeah.
So you need to grow this crystal. What neutrons before you?
What?
Neutrons.
Neutrons.
Yeah, neutrons do the same thing. They make the.
Yeah. So you would have to basically, I mean, you know, so if you look at xenon or like any of these experiments, right, you veto on everything else. So you would have to essentially do all of that and only focus on the few events that you think are due to dark matter.
The problem here is that since you have this long wave defects,
Yeah.
your neutron background becomes accumulated. You know, each time you are running, you take out, you look, and then next time you have more neutron, more neutron. So this is different than differential rates.
It is. So you know, like in a sense, right, this question of like how much time you need to study it is a very quick function of how well we can get our initial localization. So the initial localization can be done, you know, to within if it's about a millimeter, we need about a day to study it. But if you bring it down to like a micron, then it's very rapid.
In other words, your crystal should be grown underground. Otherwise,
oh, you mean the actual creation of this thing? Oh, fair enough. Yes.
Other questions? Very nice talk.